Okay, this is going to be showing you do principal component of analysis, PCA, and using a Python for this. So I hope you enjoy this. So let's switch screens here. All right. Can take a look at this. So this is an example where principal component is very useful because generally the idea with principal component lies into reducing the number of dimensions you have to work with inside of machine learning. And by reducing the number of dimensions for this, significantly improves the speed of this. But when you do this, you want to be able to maintain the key characteristics you want to use for this. So this is the reason why PCA is a very common traditional technique for it. By lowering the number of dimensions here with it, we can, but still capture the importance features and discarding less significant features for this. So this particular example we're going to be working with is that I just grab a figure here with it showing a flower, and there's three types of uh, flowers we're going to have here. For this, where it has a pebble and sepal with it, and they're measuring the height and the width of this setup here. And this is what the table looks like here when we take a look at this, sort of the design of it. You know, from the markers they have for each one of these features of this particular flower with it for it. And you can see that it's four-dimensional. But then this should be a lot more work with it. So we want to be able to reduce this from four dimensionals to less dimensions. So the question is, how do we do this? So this is what we're going to be going through with this, the actual design of this, moving with this technique with it, showing this. So I'm saying typically with it, most people use two-dimensional, sometimes three with it relationship, but we're going to justify how these dimensions are selected. So the very first step we're going to do is load our data set here. Um, so running this data set itself, we're going to actually take a look, and I want to make this a little bit bigger for you guys. So now running this data set here, and that we have it actually loading up. So we import a pandas PDA for this, a NumPy, and we'll just label it as NP with it. This is used for plotting. We have in the design here, and then NSC born with it. And the SK imports the data set, where our actual data set that is built into actually Python. It's a very common data set for training for things, containing those actual flowers itself. So that's why I'm saying is I'm loading up the errors for this dataset.load errors. So now we have these few features in that. So taking a look at this, running it another step here, we have these four columns with it, and we saw that previously up here with these four columns containing these measurements, which is quite useful. Other features we will take a look at is that, remember I was saying the three of these are going to be following us around, or and not the target feature names we want to work with from these measurements. So, and this is what it looks like inside this data set right now. It's 0, 1, and 2. 0 for this one, 2 for this one, and 3, sorry, 0 for this one for this, and two for this for relating to it, which is fine. But when we plot it, we want to be able to have a clear image so we know right away for this. So this is what we're going to be doing in the next step, setting this up here. We have the target names. So we had 0 assigned to this. Whenever we see a 1, we have this, and this is set up here. We will be putting the data in a data frame for this, and this PD for this. This was mentioned up top here. We're executing it. So we have the iris data we have in there, which is good. And then we put the name of the columns here for it, the name features of the main columns, which is quite useful. We saw this on this line here when we display it. So moving along here. Now, when we have this actual data we have loaded up here, we have this iris target name, what it is, which is just the 0, 1, and 2 for the column. However, we want to change that to useful names here. So when we created this column here, target, we say target map target names for this. And this is the target names in here for this. So these numbers here will be replaced with these names here. So let's execute this, and we're going to have a plot here. And just to let you know here, remember the LPT is for plotting. I have this up here, loaded up in a previous library. That just setting the size of this figure, I wanted to control it. And S and S, we declare it up top here for the target name. So we have the target names here and the actual data, the data frame itself with us, and label it. So we can see in this actual data set is that there is 3 of these, each about is 50 of them, totaling about 150 for this count. Now keep these things in mind when we're doing this. So moving along here, this is that now we have a good understanding what this data is and to set up this data for it. Now let's start loading the features and target things separately. So now I said iris data, put it into the X value, iris target, what it is, which is being declared up here earlier, remember? For this, making sure we have the right shape. So we know that it's 150. Remember, 50 plus 50 plus 50 makes 150. 4 columns, what it is, and that as the height and the width we have here for this. We know it's 4. So then the Y, we're loading it up. We know it's 150 because of the target names we have in there for the total of these actual. So that's good. Now our data is actually set up for this to start to move us forward to do PCA analysis for it. So this is what we're going to do here. Generally what we do here is a good idea to get into habit when we're doing these machine learning techniques is to scale the data for this, because if one of the columns you are trying to work with is greater than the other ones, it will favor the greater column, and you will not get an as accurate result as if they're very close together for this. So this is what this feature is here for. It's a standard scale here. And I wrote up some text here saying that it's using for scaling the data for this. And we're going to be using this throughout. This particular scaling technique is very useful for keeping things united because it uses the mean and variance for this calculation. And also too, since we're dealing with PCA, so we have S key learned for in here and PCA, which we're going to have follow throughout our setup here. So let's execute this library and that. So everything's been successfully loaded for it. And now you remember this X value here? And that was our original data we have in there. We're going to be scaling it here. So we have the standard scaler, which was originally called up in this library here. We fit it and that. So we tell it, please scale this data. And look what we have now. Look at this. It's more closer together for the setup here to work with things, keep our useful information for it. Because remember previously what it looked like? Values like this. Now keep the main features because we can reverse it. That's the good thing about this, but it's more useful and easy to work with. So now the original question is that reducing the dimensions here for it. And we even need to be able to make a good decision about this. Well, first we got to look at the data here for getting an idea how much we can reduce the dimensions for this. So right now I have it as n components as 4. And the reason why we have 4, because remember we have height and width for this actual data for this. So we have this set up here, and that's why I picked the 4 columns for actually executing it. So taking a look at it, it's 4 with it, created this actual PCA, what we had in the import library up top there. And that we have declared here, which I'm referring to this. And that we say the number of components 4 with it, X scale. Please take that data and put it into this PCA that we've been transformed. So let's run it. So now it has executed it, but you're saying, okay, great. We have these values all set up here, but I still can't see where we're going with this. Well, we're still going to be working on this to get the key number of features with it because we have 4 dimensions right now and we want to reduce it. So the next step here what is useful here. It's actually seeing the PCA explained variance ratio, which we're going to be going back to a fair bit, number of times with it, um, which explains the actual ratio features we have in there. Gives us a very important information here. So when the total ratio variance is actually based off an eigenvalue divided by the total eigenvalues with itself, which eigenvalue, depending what you're taught with it, allows us to be able to set a value and allows for scaling with it, which is quite useful for this. So we get the what features the information about these variables with it. The explainable variance for it, it's called values. Later on, I will change the name on it, and the comes some ratio with it for this variance. So it's accumulating it up with it. So executing this, get the values loaded up here. I just reload NumPy NP again, just to keep things going on. We reload this for the actual design here. We did declare it up top here, but I'm just trying to make sure you get familiar with it. Then PCA dot a number of components, which we declared up top there, where we set it to 4 with it, and I do a +1. And the reason why I do a +1 is that the original, it starts at 0, but I just wanted to make it easier to see, so I just add 1 into this actual. So this is the number of principal components, PC components we have here for it, and we expect 4, because that's what I set up top here, where that's the number of components here. Then the figure size we have in there. And then let's plot this actual results here, what we get in here. The principal number of components with it, proportional ratio, which we got from here with it. And I say red, and I put a circle so you can see dots with a line through it. This. I also give it a title, and I will explain why I put the title album mean method screenshot with it, set a font size, the number of components along the x-axis with it, and the proportional variance we have it for each one of these design here. So now moving along here, we see here that we are able to capture a lot of features at this proportional variance for 1, a little less here for this, and less and less and less as we move along here. And that one. Now, deciding the number of principal components we could use in that, the common, there's 2 common techniques. The first one is an album method, which is commonly used here to decide how many important it is. It involves seeing that as we see here, this captured a large number of features we need here to understand the data set. And as we start moving along here, we start seeing less and less variance of this. So it starts leveling off here. From here it starts and then it goes along here, really a lot of leveling off here. So in this case, generally is that most people would say, okay, I want the first component and the second component with it because it has the most variance and captures the most features, and I can discard the minor other features and still get useful information here. But I would going to explain another one called a Kaiser method with it, and it would support your argument a little bit stronger than saying that I'd say 2 principal components, all I need to use compared with the 4 with it, which is an alternative. And the Kaiser method with it, compared to the album method, what I was just describing here, explains generally they say with this variance, anything greater than 1 is what we will keep for this. It's just the general rule they have in there. So let's do an example here so you know what I mean by this actual 1 here. So taking this actual example, we'll do the same thing here. Just import some libraries here for it. And then the explainable variance, we have this. So we're extrapolating the key features we need in there. Figure side, we saw this PC numbers before, and variance here, which is up here at the design of it. Same thing, we have we make a red line, the old, with it, and a straight lines connecting it. I give it titles, number of components, variance. The one thing that is new here is I have a y equal to 1 here. And I purposely put this actual blue line here across here, running across here as a dash, so that you can actually see the actual 1 running across here. So it's very clear and evident to you. Then I say grid, I want to show it and show the example here. So now executing this, we see here with the Kaiser, what it is. Anything greater than 1, we accept here. Now, this is very, very, very close. What it is, so we're going to say here, this is acceptable here. And that with it, that fits the rule, first two components here. And that. So, so far we have a very strong case that is actually quite useful, that two components here. And I'll show you one more, just in case what it is to set it up here, because I'm a little worried that when I was telling you about that, when they starts leveling off the previous one with the elbow one, leveling off starts being more consistent, we ignore this feature. This one makes it a little bit more clear here, which is actually a cumulative sum of variance. There's an example here for it. So I wrote some text up here just in case you are not comfortable with it, but we use the actual feature of cumulative sum, what it is. So grabbing the essential results, and we can start seeing it build up here for this. So taking this, we have this, we changed now to, we have this already declared here, a bar within the range of this PC variance, so along our x-axis and that, +1, because I don't want it to start at 0. I want this to set up at 1 here, like I've had in this actual setup here for plotting it. And the same thing along the y-axis, the number of components here, what it is. And I use CumSum to do accumulating up for each one of these principal components here. And then I also do a plot line here for this actual line, for this red, for the, assume it, see this, and you'll see a line up top above each one of the bars being added up for this. And I just put a legend here so it's a little bit clear, added grids, and show things. So let's take a look at what I've been talking about, this cumulative sum here. Notice that this is a very high, what it is, which is impressive. You can catch a lot of the features here, and a lot of the other features in the side of the setup here, and less features here, And notice here, first component, principal component here, second component here with it, and then it pretty well starts leveling off here. And that one. And so we have 3 examples that supports that two principal components captures most of the main features, and we can ignore the lower dimensions here for it, because we will be able to work with it and grab the key points we need with it and that. So now we have established that. We have to repeat this process again, or actually in that. And that. So this is where I show in here, it says the principal component using 2 principal components, because we accept what it is, and we reset this. The PCA, number of components, 2. Previously it was 4 with it, but we established this and that. So let's run this code here. And so we have 150 and 2. 4, it was 150 comma 4. What is this? Because we had 4, but now we have 2, which is good. So this is a shape here. And we're going to actually now start seeing how this is set up here, where we're going to be plotting out the principal components in a scatter plot with it, where you can see each one of those 3 variables I mentioned here earlier, where we had labeled for actually working to make things clear with it. These 3 here, we're going to be actually putting them in a scatter plot and clustering them very clearly based off the height and width measurements of those 4 columns we were talking about, where we have reduced it to 2 now. 4. We take the X scale data we have transformed with it, put it in the main features for the actual setup here. The PCA data frame here, we did put the actual setup here, which we have in there. 2 columns, great for this. We've done this before with it, changing the names around so they're useful, so it's very clear what we can be labeling instead of having 0, 1, and 2 for it. And just like before, we do the same mapping for the setup here. I put this in here just to get the head amount of data for this and that. I set the actual size of the figures we want in here and the label sizes for it, so it's very clear for actually seeing it instead of being very small. And then the x-axis is PC1, PC2, 2 principal components, actual data here. And I set the height and width of everything here so that's clear that what we can see for this actual data when we're scattering it out. So instead of little small dots and making it. And then I plot it out here. So now executing this scatter plot will take us. See how we have in here for this and that. We can see very clearly the three of them, how they're broken up and how they are working together, how they're similar, how they cluster together, how they're not clustered together for this actual setup here. And that. And that's just from taking 4 dimensions to 2 dimensions. Now, to actually see the correlation between this, actually, it's quite useful with it because we want to be able to see which one of these, the actual features in that will actually have a direct effect on the other one for this. And what they use for this, to make it clear, is a biplot for this. And then we're going to go through this example. Now, we have this PC here with it. I never stressed earlier, so I'm going to show you here for it. We have actually declared this up further before, this PCA. So you know what's in this. It's further up the code. So I am just moving up here for this actual design here. So this is our actual earlier scale data. I just put that in there to make it easy. You could repeat this step if you want what it is, but it's just taking the 2 components of data and scaling it with it for it. So we're taking advantage of this, what we have here. So let's move along here for this. So we have this biplot. We take all the rows of the first column, and in Python is that we just can't put a 1. We have to put a 0 with it because that's how it does the index with it. And then the second column, which is 1 because we started with 0, and put it in the setup here. And that we have the PC components, so loading, extrapolating the associated values between each one of this for actually this. I'm going to execute this. So now we have a loading feature, load up here with it, and that, the features in itself. And we have the actual data stored in the setup here, which is fine for this. So we have 2 columns and the 4 main features, components we have in there. So now we have to plot this actually. So we're going to illustrate how the principal components and show the actual how these various lengths and weights are actually being correlated for this. So I put some text here in case my explanation is not very good enough here. And that. So we have the loading features. So first column, second column, what it is for the actual design, which makes sense. We have the X values and the Y values here. The iris name features itself with it. We've defined it up top there. We've gone through it, bigger size, and we go through each one of these for this because we're going to have 4 of these columns for this. We do a scatter plot here. And make the S is that you're going to find in there is that you have a line with an arrow pointing out with a circle in there, just making a little bit emphasis here and the size of this. And that, I want the coordinates to be starting at 0 with it, and grab the data and plot it for each one of these. And that, we have the color of the reds. You're going to see what this is soon with it. And when this is just actually showing what the arrows is for this. And then it's one thing to have the arrows, but we need to be able to associate with these arrows the names with this. And this is what this is, the variable names. Please plot the names so I know what I'm looking at with it. The line spacing here, I actually, in this particular example, is I restricted the x-axis and y-axis, so we have a very clear picture here. So we start at negative 0.8 for this actual and run it through. And that, and all the way up to 1.25 for it, and plot the value. So this, I've been talking about this, so let's take a very good look at this, what we have here. See what we have here with it? We have the arrows, clear what it is. And that, so we can actually see in this picture what it is that the pebble width and the pebble height have a direct correlation because as that changes very much with it. And that, the sepal length does have some influence here for this. This one, when it goes in the other direction, doesn't have as much influence as it is with it because it's not as correlated for the setup with it. If you're tying more with this, then you can almost say that they're less correlated as they go further out with the 90, but you get the general idea and how to stand on this. And this is just 2 principal components here. We can see the x-axis here, negative 0.8 with it to 1.25, the same with the y, which is actually what we did here for the steps here. So this is very useful information here for gathering more information about our data itself for it, from taking a 4 dimension to 2 dimension and getting a better understanding what our data is behaving like and what we should be able to understand this for this. So now the question is that why don't we combine these two setups with it? The biplot and the scatter plot, we can do that actually itself for this, which is going to be the next part here for this by combining it with it. So we do the same thing here. We load our data set up here, get our data, turn it into a data frame, our names relevant with it, a Y value, what we're dealing for this. So take a look at the data here. We can actually see this is what this head is showing is this the top part of it, not the tail, but it's the head of these setup here. So we have this data, which is fine. Then what we're doing here is that I made a copy of the actual data frame itself. And it's just a feature here is that I find is that sometimes what Python does is that I change to the original one, it affects everything else with it. So I usually do a copy, say, please make a copy of our data and keep the original and let me play with this for it. And so to make this fit better with the two of them, we had to scale this actual design. I'll be able to scale the two of them for this to make sure they overlap and fit together. So this is what I'm doing with the scaler here. I say I take the maximum minus the min and get a scaling feature with it and just index through it for these values for it by multiplying. So make sure we can have everything fit together. And that. So moving along here, I just reset this as in here so that we're able to have a very clear picture because I'm always worried about previous pictures might interfere with the actual plotting. So we have our loading values, which we covered earlier here, the X values and the Y values in our columns because we have a 2-dimension. And that we do the same thing here for labeling our X-axis and Y-axis and the data we're going to be plotting here for it. And then we have these, I put these colors in here to make it very clear when we can start seeing things about the lines for this. As we do our traditional, what we did before, the previous one, our scatter plots with it, set our coordinates at 0, X and Y with it. And you're going to see here with the red lines for this and the arrow, text names, same thing. This time I just restricted the line spacing here before it started in the same position, but it ended before at 1.25. I just made it 0.8 just to have a very clear picture for this. So let's execute this. So remember having a biplot on top of each other. So we can see actually here very clearly with it. So these are colors with it I had in here. What we make it clear to something more. And we can see actually how this is centered at 0 with it and that, and how it actually clusters around a lot around here for the actual setup here. But so this is very useful information. But say we also wanted the actual take in these values here, and we wanted to put the actual numbers that are associated with it. So we find it to be able to say, okay, well, I know this is supposed to be here and that with the numbers, and I've related to the data. So we can also do that too for the setup here. So we have to do more scaling here. And that, like before with it, PC1 max and min with it, the values for scaling it. So we're going to execute it. So we're going to find it useful with it. PCA number of components, extrapolating the main loading features we need in here for it. Transforming our scale data with it. You can see I do this a lot for actually making sure it's transformed and set up with it to make it useful with it. You load up another variable and use with it, but I just find it easier with it. For the score with it, we're going to be essentially repeating the same things as before. The size with it, our arrows and long here with it, and that. This is just a weight I put in here. You don't have to do it, but I just put it in to make it useful, to make it a little bit clearer for myself for it. And then the PC scaling for the scatter, sure our data actually things are lined up better with it. And we start labeling all our data points for this with our actual value. So let's execute this, and you'll start seeing this scatter plot here. We have the same red. Now this time it's all red here, which is, I never stress this as much for the actual arrows here, but I made everything red. And you can see all the numbers here associated with the values here with it. Just something some people have found useful with it. So now we've been actually showing in here that everything is two-dimensional with it. You might say, well, I still would like the three-dimensional. I understand what you showed with the Kaiser and the elbow and the cumulative sum with it, the two components, but let's just see with three with it for it, which we'll do in the next part of our explanation here with it. So now we have to change this. Remember, we first start off with 4. Now it is actually, the previous one was 2. Now we're going to do 3 components. So keep this always in mind with it because it's easy to forget. You are extrapolating features from our PCA for the scale data with it. That I print these values out here for just for shape so you know what is going on here for this. You'll see what it is, the actual shape before and after we do this scaling with it. So and that, start lighting up our data frame with it. So before we had PC1, PC2, but this time we include PC3 because we're doing a three-dimensional here. This is a repeat again. So let's execute this. See what we had here in the sprint. We had 4, the 4 columns before, and now we reduced to the 3. Great. Now let's get an idea of what we're going to be doing here. And that you have to load up this libraries here for doing the three-dimensional axis with it because we're moving from 2D to 3D setup here. This is just me experimenting with some things, but I commented out, so don't worry about it here. We have the iris names, the target names for this actually. Remember, we're trying to get the names of our data instead of the 0, 1, and 2 setup with it. Did a copy of our object data with it. Our data frame itself, doing a copy of it for it. Labeling our information here, PC1, PC2, PC3, so you can see along the axes and that, do our scaling, make sure it fits, and that, multiply it out for this. And this is just actually setting actual sizes we want here, or be able to see it with it. I like doing that instead of having small, certain I can control the size here for it. Final labeling of our data for it. The Gatto this would be actually the data points, a scatter plot with it, the actual values itself. And then we'll start working on doing our loading features and our biplot inside this actual setup here. This is just me trying to keep things center, work it. I found it very useful to make the picture much clearer with it. If you want, you can play with it yourself. Board. So let's execute this. And look at our biplot here for this. We have the same thing moving along here. A bigger picture with it, and that just in case you want to be able to see the actual design, but you can actually see this is a three-dimensional. Some people find it very interesting. We can see how the advantage is that how this, the 2D, we saw that these were very correlated together, but we can see that it actually pulls away a little along here with it, actually useful with it as it goes further out, and that's shown in our setup here for our 3 components. Principal component 3, principal component 2, principal component 1 with it. So these are the references I used inside of our actual to pull this all together with it. They're quite useful with it. If you want more information, here there's a lot of information on the web together with it, but there's just a few of them for it. So now I'm going to switch screens, and I'm going to say thank you for listening, and I hope you enjoyed it.